I am developing the analogies that, according to paradigm theory, exist between the practice of solving puzzles like chess puzzles, wood puzzles, and other stuff, and the practice of normal science. And the first one that I developed was that there's an implicit set of rules for both activities which constrain the solution process, and there are criteria for the identification of completed solutions for both activities. Now, the next analogy is also a very interesting one. And that says there is an expectation of the existence of a solution. Just think of chess puzzles, for instance, first. It's very important that you believe in, you read your newspaper on a Friday or a Saturday and you are an enthusiast of chess puzzles, that you say, yes, I know this problem has a solution. It's very important, otherwise you wouldn't start doing it. If you didn't know it has a solution. Well, there are some games, solitaires, in which it's not always clear whether there is a solution or not. Therefore, some people dislike them. But in most of the games, like these puzzles or Sudoku or so, of course you assume that there is a solution. And that is the same in the practice of normal science. And again, this practice is therefore very different from other forms of practice. You expect that there is a solution, right? And there may be the case that you try to find a solution, and then the question is, how do you react? What do you say? So if one fails to achieve a problem solution in a chess puzzle or in a puzzle, Sudoku or whatever it is, it's very simple. If you tell your friends, I couldn't solve the problem, then your friend will say, if he's frank or she is frank, yes, very simple, because you are an idiot, right? And therefore you couldn't do it. Because there is a solution and you couldn't get it, so you're just stupid. Sorry to say, you're a good friend, you're very nice, but you're a little stupid, you couldn't do it, right? And something very similar happens during normal science. Because people expect that, say, you have a certain problem in atomic physics, that on the basis of Bohr's model of the atom, say in 1916 or 17, one should be able to solve the problem. And if you can't solve the problem, there are two ways how this could have come about. Either the problem was badly selected, right? You have a framework for the solution, but there are still problems which cannot be solved because they are too complicated, for instance. And one of the very important points of creativity in the sciences is that one can identify problems that one can solve with the resources you have, right? If you in your master's thesis get a problem where you have to investigate 10,000 different plants, you know, within 3 days, you can't do it, even if you're very industrious, right? And all of you are extremely industrious. I know it. I trust you, okay? But you still couldn't do it, 10,000 in 3 days. It's just impossible, right? Therefore, you must pick a problem which can be solved given the resources that you have. And if you have to do 10,000 cases within a month or whatever it is, it's just not doable, right, in typical cases. So if you can't solve your problem, it can be because you have chosen, you have picked the wrong problem. For your master students, it's usually your supervisor, all right? It's not you yourself. But once you are in science as a free-moving subject, you know, picking your own problems, then it's your fault. If you start working on a certain problem and you can't solve it, it can be because you picked a problem that cannot be solved with the resources you have. So who's the idiot then? It's you. Very simple. Like in the chess puzzle or something you can't solve. You either, the problem was badly selected, or you failed to solve a solvable problem. Either the problem is solvable or it's not solvable, right? If you picked a problem that's not solvable, you are the idiot. If you picked a problem that's solvable and you can't achieve the solution, you are also an idiot, right? So whenever you don't succeed in normal science, it's you who fails, no one else, right? That's the interesting case. And that is because you expect there is the existence of a solution. Once you are in the face of normal science, that means once you have paradigmatic solutions to scientific problems, to which you model your own problem solutions and your problem selection, right? Once you do that, it's all your fault if you don't succeed. If you look at a different situation where this is really different, now look at the activities of President Obama with respect to Israel and its neighbors. So, if Obama also fails, as all the other presidents have really failed, I mean, there was a Peace Nobel Prize, but it didn't last very long, then it's not clear that it's just Obama who is just not good enough. But people will say, possibly the problem is unsolvable at this point, right? It's not just Obama's fault, it's just unsolvable because these people are in a state that a solution, a peaceful solution to their political problems just doesn't exist. And Obama is not... cannot produce wonders and miracles, so he couldn't solve it as well. So there are many problems in real life where you don't have the expectation of the existence of a solution. You hope that there is a solution, but you don't really know whether the solution is realizable. Yeah? You just don't know. So if somebody tries to do a solution, you say, you are very brave, because there's really a chance that you don't get a solution, and then you failed. But the point is, in normal science or in these puzzle-solving things, it's quite clear that there is a solution. And if you don't achieve the solution, it's always you who failed, period. Right? And that is, again, that's something which is, of course, to some degree fascinating, both in puzzle-solving, in the literal sense, so if you are a fan of chess puzzles, but it's also, or Sudoku, or whatever it is, and also in normal science, because you know, if I do the right thing, I will succeed, right? If I'm brainy enough, if I'm clever enough, and I choose the right problem, there will be a solution. I can achieve it, right? I got to do it, right? And that's a fascinating challenge for some people, for those usually who stay in science. That's the challenge, you know. There are the problems, and I can achieve the solution. If I don't, then it's my fault, so I better work hard and get the solution. But there is the hope that there is a solution. You know it. It's more than a hope. You just know it. There is a solution if you pick the right problem. And that's the same in puzzle solving. So again, this is something which is it's not a very obvious property of normal science, but this property of normal science becomes explicit by the use of this analogy, the analogy to puzzle solving. Okay. So there is the expectation of an existence of a solution. Again, be aware that this is very specific and that in many other occasions in life, this does not apply because there is not clear whether solutions exist or don't exist. Okay. Here's the next one. And again, this is perhaps surprising, but it seems to be really a right description of what happens in normal science. The research activity does not aim at innovation of the guiding framework. In other words, it takes the paradigmatic solutions for granted. Okay? Let's go to the puzzles first, where the point would be that the activity of solving the puzzles does not aim of producing innovations in the guiding framework. That means the rules that define the puzzle. And this means the following. If you have a chess puzzle, it's not the suggestion that you say, oh, if the pawn may also move backwards, I could produce a wonderful solution. That's a great innovation for chess puzzles. Right? People will say, no, sorry, that's not a chess. What you're doing is something else. You're not solving the puzzle. The puzzle means stick to the rules, period. Right? It's not suggested that you change the rules, right? Or say, oh, this figure here now can move anywhere, right? Immediately. That's not the idea. It's not the idea that you reinvent a new game of chess. No, that's absolutely not the idea. It's absolutely conservative, right? When you do Sudoku, you may say, oh, I'm only allowed to use numbers 0 to 9. Why may I not use pi or 17.5 or something? No, it's not allowed. It's not a question, it's not an invitation to make creative innovation. It's simply not the case, right? And that is the same in normal science. Once you have your framework, you are not invited to change the framework radically. and innovate it, make an innovation. So for instance, you work in the tradition of atomic physics from 1915 to 1922. You are not, it's not suggested that you invent a new model of the atom. Not at all. Because the activity of normal science during that time is defined by Bohr's model. It means if you do atomic physics, you've got to do within that framework and not change fundamentally the framework here. That's just not the rule of the game. In the same way as in puzzles. It's simply not the game that you change the rules, but the point is you stick to the rules and use the rules creatively in order to solve the problem. Right? This is also a rather hidden aspect, because many people associate simply with science, oh, innovation and revolution and all that is simply not true. Just look at your master's thesis, right? Whatever you do. It's not the question that you initiate a big revolution in horticulture science by your master's thesis, but it's usually that you stick to some rules and you have a framework in which you do your research, usually. Well, you'll tell me then later in the oral presentations about your master's thesis. So the point is here that paradigm theory says the idea that science is innovative has to be restricted during normal science. It is right that you have to have new ideas when you solve a problem within the frame. For instance, coming up with the idea, oh, I don't use circles only, but use ellipses as well. But that remains within the framework. You're not revolutionizing the framework. But if you said, for instance, oh, I hate electrons as discrete charges. I want to have a cloud of charge, right? Completely random or whatever. Then people would say, sorry, this is not atomic physics what you're doing, because you are leaving the Bohr's model. And atomic physics between 1915 and 22 is using Bohr's model, period. Right? So we have a similarity here, again, or analogy between the research activity and puzzle solving, namely that you do not aim at innovation of the guiding framework. In other words, you take the paradigmatic solutions for granted. You simply accept them. And when you do exactly the same, when you solve chess puzzles, for instance, of course you've seen other chess puzzles, and of course there is no way of saying, oh, this chess puzzle, the solution of this chess puzzle which have been published, no, I don't accept that. No, I don't like these rules of chess. Then you're doing something else. You're not solving chess puzzles any longer, right? And that's the same here. If you work in atomic physics during that time of Bohr's model, you simply have to use Bohr's model, period. No alternative. No big innovation asked for. Okay? So that's the third sub-point here concerning the analogy between between puzzles of all sorts and normal science. Here's another one which is also surprising, perhaps. Namely, contrary to inductivism and deductivism, the research activity cannot be seen as testing or confirming the guiding rules of science. Leave the rest. It cannot be seen as testing or confirming the rules of science. If you look at inductivism, in inductivism you are told, look, what you do is you collect data without unbiased, you collect data, and you use the data in order to confirm then certain hypotheses, to inductively confirm a certain hypothesis. If you look at deductivism, it looks similar. Why are you collecting data all the time? In order to test your hypothesis and theories. Well, that's the idea. Here we have the theory or the hypothesis or the model, and deductivism tells you you've got to test this model, and therefore you collect data in order to test the model. Right? It's confirmation, it's positive confirmation or support for a hypothesis in inductivism, and it's testing, negative testing in deductivism. Now, paradigm theory says this is just the wrong picture. The activity of normal science is neither confirming a hypothesis nor testing a hypothesis, because the hypothesis is taken for granted. Right? That's the difference. When you work in this model of the atom, you are not neither trying to confirm the model, nor are you testing the model. You are applying the model. And that's different, right? So, and here you see already a solution to a problem that I hinted earlier at, but I come back to that in more detail. So contrary of how inductivism and deductivism describe the practice of science, you know, when you see that scientists collect data and do different things and connect them to theories and so on and so forth, and deductivism and inductivism describe that as, you know, either confirming a theory or a model or testing it, then paradigm theory says, look, this is not the reality of science. The reality of science is different. You are not doing that. I'm not saying positively now what you're doing, but now let's remain here. If anything is tested, it's not the model, it's the scientist. And this is funny. I mean, now look at puzzles first. If you solve a chess puzzle, you are neither testing nor confirming the rules of chess. You are using the rules of chess. But it can't be the result of you solving a chess puzzle to saying, oh, the rules of chess are very good, or they are very bad and I want to criticize them. No, you either solve the problem or you don't solve it. The question whether the rules of chess are good or bad is just not the question that's being asked when you solve a chess puzzle. That's just something else, right? It's a category mistake. It's something different. It's just the rules of chess are given, and then you solve your problem, right, and enjoy the solution. And it's not a question that you say, oh, this chess puzzle confirms the solution of chess. No, that solution, the rules of chess are simply given. They are not up for a discussion. They're not up for a discussion whether they are good or bad when you solve a chess problem. It's just not the case. And that's the same here. When you move here in the tradition of normal science of Bohr's model, then the question is not whether Bohr's model is good or is bad, but it's taken for granted and it's used for the solution. And that's a different sort of activity, right? So if anything is tested, it's the scientist. If you say, I want to describe science as testing, then paradigm theory says, yes, that's a funny way of describing it. You may do so, but the only thing that is tested is the scientist, as in the puzzles. What or who is tested when you solve a chess puzzle? You are tested, whether you are able to do it or not. Nothing else is tested. And that's the same, according to paradigm theory, in normal science. If you want to describe it as a test, then it's a test of the scientist, because the scientist is either able to pick a problem and solve it, or he's not able to pick a problem, or she is not able to pick and solve a problem. Then it's her fault. Right? It's not a fault of the model. The model is okay. It's just the question whether you are able to pick a good problem and solve it. And if you are not able to do it, then it's your fault. So who is tested? It's only the scientist who is tested. Right? That's the point here. If anything is tested, it's the scientist. And the whole focus of the research activity that is given to the research activity in inductivism and deductivism, paradigm theory says is wrong. Right? It's not science's main business always to test or confirm theories. This is just not true. That's just not what scientists really do. Even if you imagine they could do it, but they don't do it, in fact. What is done is the production of new knowledge on the basis of already existing knowledge. That is the activity of science, says paradigm theory. And again, take the example. Once you have Bohr's atom, and you have solved the hydrogen problem, meaning calculating the spectral lines of hydrogen, then you say, I'm using this achieved solution as the basis for my next research activity. Namely, picking a problem that's similar to the hydrogen problem, and then solving it in a similar way than the solution of the hydrogen problem proceeded. That's the idea. And that means you are producing new knowledge. For instance, you start then to calculate, this is the H2 problem, this is here H2, and now you start with fluor, for instance. Right? This is an atom that can be, is it Fl or F, fluor? You know, the Fl, fluor. Okay? That's better? Okay. I learned some chemistry, I've forgotten it, more or less. Anyway, fluor looks a little strange, but at any rate, some other element, whatever it is. Or take, if you don't know that, I know that iron is this one. All right, and then you may say, okay, So let's solve the spectrum of iron, which is very complicated, in fact. But someone may say, okay, let's apply that. And that means when you do that, you are not testing, right? You are not testing Bohr's model. But you take Bohr's model for granted and say, look, I know how Bohr's model works because I know it for hydrogen, and now I want to apply it to something else, namely to iron, right? I want to apply it there, and that means it's no testing of the model. Either you succeed or you don't succeed. If you don't succeed, you've been tested, right, as being an unable scientist, because either ferrum is just a very bad, because it's a complicated atom, and you should have chosen a simpler one, right, if you know its name, for instance, fluor, right? So you better choose a simpler one instead of ferrum, because ferrum is very complicated from the electronic structure, whereas fluor is simply there's one single atom in the outside, therefore it's so strongly reactive. So I know the property of that damn thing, but I don't know the abbreviation. Okay, at any rate, the point is then that what paradigm theory says, look, inductivism and deductivism are somehow fundamentally misguided because they describe the relation between gathering data and some theory always as a confirmation or a testing. And that's just wrong. It's different in science. What people do is they gather data in order to produce new knowledge on the basis of already established knowledge, and established knowledge means on the basis of the paradigms or paradigmatic solutions, that have been achieved in the beginning of that phase of normal science. That's the idea. So I think this is a very rich and again a very insightful description of what happens in many cases of normal science. And of course that's the same well, that's not exactly the same, because usually when you do a Sudoku, you do a new Sudoku. Well, you may use something if you've got experience with Sudoku puzzles. Of course, you are faster than someone who's unexperienced because you know certain strategies, right, that you used and were successful, and you use them for the next Sudoku. Or if you say a puzzle solver with wood pieces, then the experienced people know we've got to start with it with a frame, right, because there we have identified certain pieces that they are at the borders, right, because they are straight lines. Unless it's a very, very, very bad puzzle, you know, that it also straight lines in the middle in order to, so if you have people you really love, give them as a gift such a puzzle, you know, with straight lines in the middle. Okay. They want to, you know, they want to be kept busy, and that's one of the ways. Then you don't have to talk to them all the time. Okay, but that's a different area of discourse here. Okay, so here is another one. And this is, again, it's very amazing, but once you think about it, it's very plausible. And that's the question, what is the motivation for people to do either puzzles of all sorts or to do normal science? And the statement here, the proposition that is given by paradigm theory is quite surprising at first sight, and it says the following, that the motivation for the activity is less the desire to possess the solution, but rather the exposition of one's ability to creatively solve problems. So, in order to make this plausible, I give you a very clear and sharp example for the case of puzzles. All right? Say you want to solve the puzzles of 5,000 pieces, where the end result is then the picture of the Kuala Lumpur towers, right? You want to see that. I tell you how you can achieve that goal much simpler. Leave the box closed and look at the picture on the box. Here you have the full picture in original size. Why go and solve the puzzle? It's ridiculous, right? Or take another example, even more ridiculous. You know solitaire, where you play with playing cards, and you play alone, therefore solitaire, right? The end result is that you get the right order of the cards, right? Ace, 2, 3, 4, 5, with the right colors. I give you a solution that's much simpler. Just go in the shop and buy a packet of cards. You get them in the right order, right? How complicated is that to do a solitaire in order to achieve that order? That's ridiculous. You know the order beforehand. It's absolutely ridiculous. It can't be the end result that drives you to get the solution. It's absolutely ridiculous, right? In all these things, it's absolutely ridiculous. I give you another example. Take the chess puzzle. Someone is really an addict to chess puzzles, right? And every Saturday, you buy your newspaper and go immediately to the chess puzzle site page, and then you work all weekend, don't talk to your kids, not to your father, not to your mother, you just solve your chess puzzle, blah, blah, blah. You know, you destroy your family life, you don't drink anymore, you don't eat anymore, destroy your life. Okay. I tell you a much more simpler solution to that. Just wait 7 days. Just wait. Next Saturday, the solution is published, right? If you're just interested in the solution, you'd sit down and wait, right? You get the solution. So you see, it's impossible for these puzzles that the motivation, the driving force, is having the solution. Having the solution is uninteresting. In some cases, in the solitaires, it's absolutely ridiculous. You know it beforehand and it's not interesting. It's not even interesting. You don't learn anything from it. Why are you doing it? Why are you doing solitaire or chess puzzles or Sudoku, whatever it is? Well, the answer here is because you want to show yourself, either to yourself and also to others, possibly, that you are an expert puzzle solver, that you can do it. Right? You can show it to yourself that, look, I have the motivation, and even if it takes me 10 hours, I'm going to solve this idiotic puzzle. Right? I want to do it. And then once you're done, you say, bingo, I did it. Right? That may be simply to yourself. If you do solitaire, I sometimes play solitaire on the computer, and I'm not telling one that I solved it. No, I do it for myself. I want to solve it, damn it. Right? Just for fun. And the solution, as I said, is absolutely trivial. The completed solution is not interesting. So you do it, the process itself is what is interesting, and the process drives you. And in the process, all you do is you say, I can do it. Now this is the same, says paradigm theory, this is the same in normal science. That mostly, not always, but mostly, the solution itself is uninteresting. It's just uninteresting. Nobody damn cares, right? And I give you, I give you an example. Say someone wants to measure the velocity of light. And we know, I think it's 299. Well, I don't know the further figures here, kilometers per second, right? Here 3, I don't know the figures here. Now imagine we know that up to, say we know it, I got to start somewhere else. Say we know it 299, and then we know A, B, C, comma, D, E, F, this is 9, G, and the question is what's coming here, right? The next digit. And someone starts a measurement and, for instance, uses 2 years to build up the measurement, right? Now, I tell you, the result will be extremely exciting. Extremely exciting. It's either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's the excitement of the result. It's one of these numbers, right? I can tell you beforehand. It may be that if you're interested here, in this one, because you have a new precision measurement, and then here the number that comes here. It's one of these 10 numbers. Extremely exciting. Wow, it's 3, not 2. Wow, I'm excited. Nobody's excited about that, but you want to solve the problem. And it may be important for applications that you know that number. But the result in itself is not exciting at all. It's boring, right? Like in the puzzles, in the puzzle case. The result, the net result of having then having the solitaire solved and you have the cards in the right order is absolutely boring. And which number it is, or even if you say you have a precision measurement and you add 2 numbers, 2 new numbers, wow, it's between 0 and 99. How exciting. I've known these numbers since I was, I don't know, 5 or something, right? So the result itself is not exciting, but what is exciting is I could do it. You know, if someone builds up this measurement, measures it, that'll be a very important thing. You get a paper in Nature. If you measure the velocity of light, and you measure it with 10 to the minus t, higher accuracy than everyone else before you get a title page possibly in Nature. Nature is the most prestigious journal, because people will say, wow, this group, usually a group of course then, was able to measure them now 2 more digits. That's sensational. It's incredible. They could do it. And you can say, I am very proud our group has really achieved that. The net result, as I said, is just between 0 and 99. So it's not really exciting. So the excitement is really of being able, right, of being able to solve that. So the sort of motivation that people in normal science develop, that's at least what paradigm theory says, and I think this is a very accurate description, is that indeed the motivation for scientists working there and sometimes working on projects really spanning decades. If you look at the big, say for instance, planetary missions or other big science things, LHC, well this is more revolutionary science, but also in more or less routine things that people invest 10 years of their life, right? And you really have the long-ranging motivations. You know that with your master's work already, which spans a few months, right? And you've got to go on and go on and go on, and it never ends. Well, it's only 6 months or so. You've got to have the motivation, right? And you've got to keep people working. And if you look, I mean, you have also external motivation. Of course, you have to finish the degree and so on. But if you are then more or less free in science, then you have to develop the motivation. And the motivation, that is what paradigm says, the paradigm theory says, the motivation is similar to that motivation that you develop in solving puzzles, right? It's that you show, you produce yourself, or you tell yourself, you prove yourself as an expert solver, as an expert in a certain game, puzzle solving, or as an expert in a certain area of science. And so the stereotype of science, that science is so exciting because there are so many new and unexpected results, that's a stereotype. It's sometimes true. Of course it is. We'll come to that when we come to revolutionary science. But mostly it's not true, because mostly you can more or less anticipate the results. And there is no real excitement about them. There is the excitement about being able to having achieved them, but not the content of the result. The content is very often quite boring. And as I said, even in these cases, I mean, if someone, I don't know exactly the figures at the moment, whether they're 10 to the minus 10 or 10 to the minus 11, if someone really increases the accuracy by 2 orders of magnitude, that'll be really a Nature paper, it's no question, because everyone will say, now we know it even better. And it's an important number, because that number goes into many, many, many calculations, and you can calculate many other things. The better you know the velocity of light, the more you know about certain others. So it's very important. But the excitement is, of course, being able to have measured it, and you have measured it and not someone else. Okay. So this ends these parallels to puzzle solving and normal science. And now, if you look back, if you try now to remove that stuff for a moment from your head and think back at the picture that you got from science by inductivism or by deductivism, right? Where deductivism, the motivation is you want to test the theories, right? And what you do is testing your theories, and that's it. Now, this is a completely different picture somehow, right? And it's very rich, and the richness of the description then of the activity in normal science derives from this analogy to the puzzles, because the puzzles are something very familiar, and solving puzzles is something you know of, you know how it feels, you know what to do, and bringing out these properties of the puzzles and making the analogy to normal science gives you a very rich and vivid picture of what normal science is all about. And you see it's quite different from from the impression we got from inductivism and deductivism. It's much richer and probably more adequate. Okay, is that somewhat clear and plausible? Good. Okay, and here's now the fifth, and this is also extremely surprising. The fifth main property of normal science, namely there is a quasi-dogmatic element. The framework is not called into question. Now let me have a look. That concerns the consensus. That comes from the consensus. The consensus says, the consensus interface of normal science says, this is the basis of our research. For instance, Bohr's atomic model for this particular example. And the consensus means, among other things, not to call into question the model, but to apply it, right, to new problems. That's the basic idea. And if you look at this now from the point of view of someone from outside, say the deductivist who says, well, science is always critical, blah, 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 and we must test all the time, then you've got to say there's a quasi-dogmatic element because they don't want to test it. If you work in the tradition of Bohr's atomic model, you don't test Bohr's atomic model. You take it for granted. And taking something for granted without testing it is, of course, somehow dogmatic. You just take it. You don't ask the question, is it right or is it wrong? You just take it. And that's somehow dogmatic. Right? Now, the dogmatism that is involved here, and therefore it's called quasi-dogmatic. This is called it's not really dogmatic, but it's something like dogmatic, not exactly like dogmatic. And there are two things why this is quasi-dogmatic. This is a sort of dogmatism that does not hold forever. There are situations in which you give up such a framework, right? This will be the transition to revolutionary science. So the sort of dogmatism that you have in science is not a dogmatism for good. It's not forever. But we will see, and this is precisely what the transition then to revolutionary science is, when people start to doubt whether this framework is really a good framework. This is not excluded. It does not happen during normal science, right? During normal science, people take the framework for granted. But there are certain events possible, and I'm going to discuss them then in the next class. There are events possible that put into doubt whether this framework is really a good framework. But then you are starting to leave normal science. In normal science, the framework is not called into question, and therefore it's dogmatic, but it's also only quasi-dogmatic because there are certain circumstances, and they happen in science, they have happened in science, they are continuously happening in science, such that you call into question the framework. That did not happen here between 1915 and 1922. People were happy with it, didn't call it into question, but I'm going to tell you then from 1922 on, people had problems with it, and they started doubting it, whether the Bohr's model was right. But that doesn't happen during normal science. So it's quasi-dogmatic because the dogmatism does not hold forever. Right? If you compare that with religious dogmas, which say in the Catholic Church they are really called dogmas. I think in the Protestant Church as well, I don't know. But in the Catholic Church they are called dogmas. And by dogma, they mean they are supposed to hold forever. Right? There is no exit clause saying, oh, unless blah, blah, blah. So Jesus is the Son of God. Well, unless we measure something and then it turns out, no, it's not the Son of God. No, that's not allowed in Christianity, right? This is fixed, period. Absolutely fixed, no way out. Well, that's at least the idea. Now, this is different, so it's only quasi-dogmatic, and there's another very important element. It is not negatively evaluated. Very often, not in economic history, when you speak about dogma, history of dogmas, at least in German, I don't know whether in English one talks the same way, at any rate. Usually when we talk about dogmas, then we have a negative tendency. We say dogmas are not good, right? Scientists at least. We're usually saying it's not good. So if scientists, many scientists are anti-religion, they say, oh, that's dogmatic, right? I dislike that. The point is that the sort of dogmatism that is involved in normal science, namely that you stick to the model, is not something negative. So when you ask, say today, physicists, do you believe in quantum mechanics? Then physicists will say, yes, of course. Yeah, and are you questioning and testing quantum mechanics? No, I'm not testing quantum mechanics. I'm using quantum mechanics. And then someone will say, isn't that a bad dogmatic attitude? Then the answer will be, no, it's not a bad dogmatic attitude because I know it's the right theory, right? So why should I continually test it? I'm convinced it's the right theory. And then someone says, yeah, but you're not testing it. Aren't you dogmatic? Then someone may say, well, if you call that dogmatic, but I don't mind, right? It's just a good theory, right? Period. And I'm not wasting my time testing a well-established theory that has been tested millions and millions and millions of times. I just don't do that. So it's not negatively evaluated. And so one must be very careful with this description of normal science as quasi-dogmatic, because it's neither negatively evaluated and it's not supposed to hold forever, right? And that's a very, very different thing, that sort of dogmatism, to the usual sorts of dogmatism, where people usually have the tendency to stick, at least they want to stick to their dogmatic assertions forever and have no exit clause. And don't say, yes, if that happens, then I'll give it up, right? But that's the case, at least implicitly, in science. The consensus is not forever, but there are conditions imaginable, and they do happen as a matter of fact, such that the dogmatic, quasi-dogmatic consensus is given up. Okay. Now, this brings this class to a very harmonious end. Namely, this is then again the question that we're going to discuss in next class. What is it that happens and brings an end to normal science, such that people start to question this framework, such that a framework like Bohr's model, and then they say, we have to change something fundamentally, because that's also a part of science. And paradigm theory has very interesting answers to these questions. So that is what we do next week. I wish you 7 wonderful working days with lots of sun, warm weather, and a very good mood.